pretty sweet.
It's going. I'm gonna be cracking. So we're starting today with an exam review. So if anyone has any questions on the study guide, let me know, and I'd like to address what anything on that means.
That was an announcement, right?
Yeah.
Hey, how much more assignment are we doing? Just general questions, so we submitted one bit, we have the part 2 to that one.
Yeah, I
And then
assume
part
we're doing
three-
part 2 and part 3 and a research paper for grad students, and that's probably what
Percent,
we're going to have time for.
Okay. Like when you say research paper, like we read one and answer questions, or are we presenting?
Read one and present it.
We have time for this? I mean, how long are the presentations? Cause I guess not on these calls. Okay, cause.
Or 10-15 minutes probably.
Okay,
Yeah, super brief of here's a cool application, here's what it does.
okay,
Maybe 30 minutes capped at most. I want to fill up maybe 1 to 2 class periods
okay,
with,
'cause I mean,
with that. So that is the other announcement for today, is that I wanna start getting people some tools for that. I have a couple of textbooks that are really just published research articles that people can pull from, and then I also want to open it up to anything out of Usenex.
okay. So,
And there just has to be an AI or machine learning application to whatever it is, but sometime by the middle of next week, I would like people to run the paper that they would like to present by me, if it's not something that's directly out of the books that I will throw on Canvas.
gotcha. So as I count it, there's 10 grad students in this class?
Yeah.
How many undergrads are there? 3?
3, I think, yeah.
Okay, so theoretically, the last class period is just all of us present? Is there enough? I guess there's a lot of minutes there, huh?
Yeah.
10 minutes,
Yeah,
so it's,
so a 2.5-hour class is 150 minutes. At 10 students, it's 15 minutes per if it's 1 class period, 30 minutes per if it's 2 class periods.
okay. Cool.
Yeah, that is the plan. I would probably also leak that into our finals period, because I don't know if I want to give you an exam over finals or not. I'll try to figure out if that's
Chris, I would give
last
you
week.
any sum of money you wanted that was under $3,000 if we didn't have a plan.
It's a lot. I cannot take bribes as much as.
Not a bribe,
Surprising.
I would drop it on the street. And I would say, oops, I hope someone whose initials are CC doesn't pick this up. And I walk. And then you're guilt-free, $3,000 in, you can get into the new magic set. That like the Spider-Man collab looked cool. Avatar looks sick.
I have to find the time to play Magic before I
Okay.
can be interested in
The
collecting.
time you save by not writing final,
Boom. Easy.
that's the time.
Writing, grading, thinking about, proctoring, that's
I
at
just
least.
throw the exams at Steven. Writing isn't too bad, assuming that I have written a pretty good study guide.
You know, I don't wanna say I'm anti-exam, but
I don't like them either, but that's what's needed to keep people engaged in a lecture environment.
No, I'm with
which
you.
is the unfortunate reality, but otherwise it doesn't go so well.
yeah, no, I understand. Doesn't mean I like.
I know, I don't like it either.
I say that giving, Eric and I are giving out like 7 total quizzes and exams this quarter. I feel like it's important in lower level classes too, you know what I mean? Like especially Cyber 101 where you can very feasibly not think if you know much and get past, so.
One question online, will the exam have something like the BaseNet practice problem on Canvas? And I say possibly.
Okay.
So something like that would be a reasonable, probably on the easier side to be in an exam environment, considering I want to test as much of the study guide as I can. And I can't have you spending 30 minutes on one problem.
Could you briefly go over forward and backward chain, just like a reminder. what it
Yeah.
is.
For this was.
Outside of the birth certificate. Okay. Was that, did they just print one off you or what?
Yeah.
Well,
Alright, so. Forward chaining was going from the. It says, from the information in the knowledge base, and then deriving the conclusion directly. And backward chaining was going from the query and then trying to reproduce the knowledge in the knowledge base. So there was also a meet in the middle approach as well, that you start with some forward chaining and some backward chaining and attempt to meet in the middle. But if we had, we can show you what forward chaining looked like in our example here. This is a little on the small side, but we started with our information on the bottom and slowly derived new facts. And then we eventually, with the combination of new facts and old facts, were able to derive the conclusion that West was a criminal, which was our query. And then backward chaining went the exact opposite way and starts with the assertion that West is a criminal. And then said that if West is a criminal, then, and derives stuff from there that are the middle points, with the eventual goal of being able to derive the supporting facts that are in the knowledge base. And once you derive all of the supporting information in the knowledge base, then you can conclude that that is true.
Then for part I, for those, how to apply, is that asking us like real implementation using predicate logic or?
Yeah, I could throw something kind of like this at you and then ask, how does forward chaining and backward chaining differ in their approaches to being able to prove this? I could have you go through it, a very simple example to throw it on what I'm aiming to be a 1-hour exam. But if there were only a few pieces of information, then actually having you derive using forward chaining or backward chaining would be okay, but I wouldn't wanna make it. This would be the cap of the size of a problem I could reasonably give you, and that's if I did all of the setup work for you. And not have you derive the logic and then apply the logic. Because if you make a mistake in the derivation of the logic, then trying to apply the logic won't work. So I have to be very careful when I design exams to make sure that mistakes don't propagate through too many possibilities. Unless you can propagate that mistake all the way through all those points. If you can propagate the mistake and then I can identify it, then that's not too much of an issue. But if it turns the next problem from something that is possible to something that is impossible because of the mistake that you made in a prior problem, that's an issue. Other questions?
For questions like M and Q, the M being how we derive mistakes logically for the first word. Pardon. Then you put universal and consistent association, implication, most general unifier.
Yeah.
Those are just things that fall under that category. Do you want us to like understand them in depth? Do you want us to explain them?
To be able to do them, so we have an example of. Yeah, before we talked about unification, we talked about. I think it was, where was it, right about there. Where did we talk about the actual? Not here. There we go. So here's universal instantiation and existential instantiation. So this was part of being able to derive anything in first order logic. Where we have this, we need the ability to take a universal quantifier and turn that into unify it with an existing entity. For all x, if x is a king and x is greedy, it implies x is evil. It's a way of saying if we can now instantiate some element of this, we had John as the example, then we'd be able to make a substitution of x for John. And that would universally instantiate this. So be able to do something like make a claim about an object based on the concept of universal instantiation, as well as knowing what it is. And then existential instantiation is the same thing for there exists. We just can't say that if we have, it doesn't work like universal instantiation. If we have an element of it, we can't know that it's true, but we can state that X is a thing. It is an instantiation of, so C1 was an instantiation of X, the element for which it is true.
But on exam, you want us to like explain it, like, I don't understand like wants to know what it means for, like, is it a comparison between we know
Either-
or
Kind of all of the above.
is it gonna be that question where you asked us about like solutions to hill climbing, and just like we have to name on and then give you an explanation.
Not necessarily, I would probably, if I'm designing a question like this, I would probably target one or the other and say. Either when is this used, or how is this used, or what are the ideas between, what are the differences between. Know them at a level that you can both apply the concept to be able to make a logical conclusion from it, but also to be able to compare, contrast, understand. But I'm not gonna have you do something that is so complex. Again, I can only assume it's gonna take you a few minutes for each question, so I can't design something at the level that is gonna be project level. Yeah.
It's like gonna apply to for Q was show where you have how for personal logic and picking out.
Yeah, so I won't give you anything more complicated than we did here for this example of,
So we have to
of resolution.
know those steps.
Yes. I would throw these steps on your note sheet. I know exactly how to do each of these so that you get something that will resolve like this. So you should be able to walk through something, a process like this, probably for a simpler example. This is kind of the cap of what I would assume is reasonable. Other questions? Any clarifications?
You also do the same for store and fetch.
Yeah. So. Store and fetch were just more low level aspects of tell and ask. So we looked at exactly how we use the employees example here for a company, employees, and individual, and then what questions could we ask based on this? So fetch can return a few different kinds of, if we variabilize the employer, then we can ask different kinds of questions. If we variabilize the employee, we could ask some different questions. If we variabilize both, if we variabilize neither, and those ended up being kinds of questions and how that information would be retrieved from the associated knowledge base. So the kinds of questions that I would ask, what are they? How are they used? How could we map the concept of a fetch to ask any of these kinds of questions for something very similar to the employee's query? What else? With some studying, we feel like there's enough information in the study guide to go prepare. Between the material that's on the study guide and what's on the slides and what's in the book and what's around.
Yeah, maybe. Like honestly, I think we'll see. Yeah, it feels pretty comparable to the last one. Are you still shooting for like that around 1 hour?
Yeah. In a quarter system, I'm always trying to design an exam based around an hour time frame.
Okay.
That allows me to target, if this class were taught not in a 2.5 hour block, we're taught in an hour block, I don't want an exam to spread over more time than that, so I'd wanna, especially given how annoying the 2.5 hour block has been for everyone, myself included. I don't know if I want to advocate for that in the future, so I would rather design something that will, the structure will map to an hour long class.
Could you go over the Monte Carlo sample?
Yeah. So general idea of Monte Carlo sampling is you're building the model based on experience. And that experience is coming from samples of the distribution rather than trying to make an underlying computation based on the distribution. You're going to simulate it, and then via the experience that you gain from that, the law of large numbers will kick in if you have enough samples, and a system that doesn't have a level of complexity, basically the ratio of the number of samples that you pull and the size of the problem will allow this system to converge eventually. Where did we end up talking about Monte Carlo sampling? Exactly. So after exact inference. There we go. Sampling before important sampling. Must be. Where did that come from? It's not showing up. Definitely after this, I felt like it was in me sampling. Yeah. So it's more like the direct sampling. I'm just gonna call that direct sampling. Where you sample immediately from the distribution. And then build up a model based on the results of those simulations. So it's useful when exact inference is either so complex that it's gonna take forever to theoretically look through and find an answer. Or you don't have access to the full distribution, you can only simulate it. Sometimes you don't know what the associated probabilities are, so you have to be able to get that experience directly, sample that experience directly, and then build a model based off of the evidence that you see. Anything else? Does that cover Does that cover that on enough depth? I'm probably looking at, that's what I care about with regards to Monte Carlo sampling. It's kind of a when would you use it? How would you do it? Why would you do it? And kind of a very high level kind of question.
I see in the slides again, I don't see Markov chain in the guys, but that's something they focus on.
Yeah, so it's in Markov chain simulation. Here we have MC Markov chain Monte Carlo. This was in we're making a single change to the example. We pick a variable and then we sample that variable and that becomes the new example. And then we pick another variable, sample that variable, make that change. So we're moving kind of in one dimension at a time. And we can show mathematically that that distribution maps directly onto the distribution that you would if you sampled every variable every time. And that just leads to increased computational speed, the ability to generate new examples more quickly. So more samples generated in the same amount of time means that you can more quickly approach that law of large numbers kicking in and increases the rate at which you converge.
So then would that be covered under like the EDX then? Is that what I was saying? I wasn't seeing it in the study head, so I wasn't sure if that was.
Oh.
Covered.
Yeah, I guess to this extent, really, it was like was uncertainty part of this?
Yes.
I think so. It was through this slide deck. It happened so long ago that it's outside of my goldfish brain.
Sure.
What else? Any other questions? Nothing else, we can dive into the last bit of content, the last, I think it's 16 or so slides before we hit machine learning. Anything else before we transition? All right, let's do it. It's been a while since we met. And so it's been a while since we talked about probability and reasoning. So we had Bayesian networks, we talked about inference with Bayesian networks, we talked about being able to come up with exact inference in Bayesian networks, approximate inference via sampling in Bayesian networks, but those all made assumptions that the underlying world wasn't changing as we are making these calculations. And what happens if the underlying world is changing? So as we analyze the problem, as we're coming up with these inferences, the world itself is static. And we know in a lot of real world domains, the world is not actually static as we do our inference, it is changing. So we are constructing evidence over time, and the samples that we get are coming in over time as well. So we need some way to look back in time and change our model as we get more and more information. And as the information that we got in our history starts to have some more context for it. So if I ask you something like, today, you're going to start taking rigorous notes on every class that you're in. How useful is it to you on exams? Right now, you have no information on this. And as you start taking rigorous notes and take an exam, you could look back at the results of that first exam. You have some evidence based on one exam, very small sample size. Was the rigorous note-taking responsible for an increase or decrease in the scores of the exam? We don't know. But as you start to get more experience with that, we can start to back into starting to see this as an entire history. And using that history as a way of understanding the cause and effect of the note-taking and the performance on an exam. So, yeah, the world didn't change unless we, the agent, are responsible for that change. But things do change outside of our control in a lot of environments, so we need the ability to be able to model that. So, we can infer the state from the evidence, and the evidence remains fixed. But yes, real-world domains are in flux. There are many dynamic aspects to those problems. So now we need to infer what is the state of the world given this history of evidence, which are really just measurements. So we're going to take measurements, we're going to see what the world looks like from our perspective, and then we're going to make an intelligent guess as to the state of the world based on what we've collected. So tons of applications to this, things like medical decisions, robot location tracking, economic activity tracking, finding the context of words that are spoken. If I start a sentence and the sentence does not make sense, as I start to feed more words into that, you start to get the context that allows you to go back and make sense of the first part of that sentence. All of that uses very similar reasoning and logic to all these other problems. So let's talk about how to do it. As always, if you make a discrete time assumption, the world is a lot easier. As soon as you have a continuous time assumption, then the logic becomes real time, which means that we need calculus. So we'll start with how to do this without the real time assumption, and then we will talk about how to turn on the real time assumption. So if the world is in discrete time intervals, then each of those time intervals counts the same amount of time. This could be make an observation based on a period between a discrete time chunk of a second or a discrete time chunk of a minute. The measurements would be lumped together in each of those discrete time intervals. And the amount of time depends on the domain. This is generally important because different problems rely on different time measurements. So if you were, for instance, looking at and analyzing the images in a 30 FPS camera and trying to figure out what is it that the person is trying to focus on with this camera, you could use a history of the images from those 30 frames per second to figure out what is the focus of this real-time camera as it's moving around, and I'm trying to take a picture of the screen in the back. That becomes you could use learning to figure out that that is the focus of what the person is trying to take a picture of. On the other hand, measuring continental drift would be a lot more confusing at 30 frames per second. We probably want a time interval that is a little bit longer than that to be able to have measurable continental drift. We need to figure out what the random variables are in this problem so that we can determine what is it that we are measuring. Some of them are observable, some of them are not. So we're going to take these variables, slice them into two large bins. The first bin is observable random variables and the other are non-observable random variables. Because observable random variables are going to be part of our evidence, and other random variables may still have an effect on the state, on the world, but it's not something that we can directly measure or observe. We can start time at time 0. Record observations in a list for each variable, so we get a sense of, all right, at time step 0, here's the list of variables, here are their associated values. At time step 1, at time step 2, and now we have a two-dimensional table of records where each row is a time step, each column is an observable variable. You could variabilize this, turn it into an object. where each object is a time step or each object is a variable. And that would allow you to more easily collapse this into one dimension rather than two. We also need an associated transition model. So we need some estimate or based on real values of how is the world evolving? What is the state space of the world? And how likely is it that given that we are in a particular state, we transition into a new state? We then need a sensor model as well. So how do the evidence variables get their values? And of course, since time is unbounded, how are we going to utilize the history of evidence to make decisions? As we're discovering, or we have discovered in our Wumpus worlds, when you have an unbounded time history, there just becomes more and more and more data associated with that history. So if we don't limit it in some capacity, then as this process goes on, we end up with more and more and more evidence. And that leads to a slower process for parsing that evidence into something useful. So to make up for this, one possible method is to use the Markov assumption that says that the current state does not depend on the entire history, but depends on a shorter history. In an ideal Markov assumption, that is, the state is only dependent on the last time interval, no past history beyond that. And in some cases, that makes a lot of sense, in some that does not. Can anyone think of a model where the Markov assumption might be reasonable? When would you be measuring something or modeling something where it's only dependent on the last time interval and not a history of time interval?
Duration.
Okay, yeah, that doesn't really depend on the duration of the last attack or it just depends on.
Maybe game modes, but like the dice rolls, doesn't depend on these dice rolls.
Yeah, so that would be independent, but for when is it exactly a history of one? So it depends on what happened last time, but not the time before that, or the time before that, or the time before that. How about something like how much brake pressure you should apply given the distance between the speed that you have and the distance between you and the car in front of you?
When is the last time matter of that?
That matters with regards to like the deceleration that you're already applying. How much more do you increase or decrease the pressure of your foot? If you're already slamming on the brake, you can look back one history and say, there's no more pressure to apply here. If you look back one and say, I'm already somewhat slowing down, how much more do I need to slow down to avoid this collision? That could depend on a time step of one, of the current rate of deceleration.
So it's almost like you're asking, when do we care about giving the derivative of something instead of the equation?
Yeah.
Change.
Yeah. So sometimes this works really well and can vastly simplify. Instead of looking over a long history, instead we look over a very short history. So I can give you an example of an undergraduate project that I worked on in a class called Markov Chain Monte Carlo. And that was the simulation of a world of organisms where their gene expression was based on, there were three variables. There were three things they could do in this very simple world. It was a 2D world. They could move, eat, and baby. Moving, they just moved in a random direction. Eat was, I'm going to check the current cell, and if there is food in the current cell, then I will consume that food. If not, I will expend the effort to consume something, like look around for food, but find that no food is there. And baby said that they were going to take the current energy that they had in their organism, split it in half, and then mutate their genome, and their genome was just the probability of moving and eating and babying. But we made a Markov assumption that said that the probability of moving and eating and babying depended solely on the last thing that they did, and only the last thing that they did. So given that I just moved, what is the probability to move, eat, and baby? Given that I just ate, what is the probability of moving, eating, and babying? And given that I just babied, what is the probability of moving and eating and babying? And this makes sense that if you have some amount of energy, rather than looking at how frequently have I eaten in the last 10 time steps, that is a complex interaction. You could say, if I just ate, it is very unlikely that there is still food in this cell. Therefore, I should move to a different cell. So I was trying to see if it could learn what does an optimal genome look like for an organism in this system, given this simplified assumption. And it turned out that all organisms had the same Markov chain at the end of a million iterations. There was a local optimum that everyone evolved into that kept them alive at that point. I was interested to see if different races would come to be where there were different local optima that could exist in harmony. And it turned out that no matter how I changed the variables for how frequently food was in the world, how much food was given, it generated different Markov chains when I changed those variables, but the entire population had the same Markov chain at the end of a long enough period of time, which was wild. As soon as there was a single mutation to that, that would either work its way, if the organism survived, work its way back to the optimum, or it would die out because that Markov chain was highly suboptimal and then the organism ran out of energy. An organism with 0 energy died. So if you attempt to baby when you have 2 energy, now you have 2 organisms with 1 energy. If they don't immediately eat and have food that's available, they die. So if your Markov chain has a very high probability of baby, given that I just babied, that organism would die out regardless of how much food there was on the map or how frequently it was repopulated. Whereas if you never babied, then that was also interesting. But then you couldn't, if you did somehow have a chance of dying out, then the entire population could die out. So you needed the ability to split and create additional organisms so that you could withstand the very unlikely chance that you did die out from a random sequence of moves that you made. So really interesting project, but the question was just, can this be modeled with a Markov chain rather than looking at a longer history of data? And the answer was yes. Not too much information was lost to prevent the organisms from reaching a reasonably optimal expression. Questions on a Markov assumption or what that means? We can talk transition and sensor models. So Markov processes can be broken down into first order, second order, third order with regards to how long of a history we are looking at. So a first order Markov process is just looking back to a history of size 1. Then second order would be looking back at a history of size 2, third order history of size 3, etc. And so the information in that length of a history will determine the current state. Stating this in a different way, the transition model is the conditional distribution of the probabilities of current values, the evidence variables given the values of the last time step. So we analyzed what were the evidence variable values last time. What does that mean for how the state of the world changes this time? That's the only thing that is an effect of that world change. So complexity of infinite possible time steps by just saying the world is time homogeneous. That means that nothing is changing about the world over time. So this would be one way to visualize what a Markov process looks like. So here we have time t-2, t-1, t+1, t+2, and in a Bayesian network, as in part A here, there's an entire history. If we're looking at what are the variables going to be like for time t+3, we have to look at the entire history. But a Markov says that we're going to, for time t+1, we're just looking at time t. For t+2, we're looking at time t+1, or in this case, we're looking back 2 time steps. So yeah, B is a second order Markov process that's going to look back 2 time steps and use that to update the current values. Questions on that?
So a good one.
Yeah.
So for it
time equals, or if we're at T, right? We're not looking back to T minus one and T minus two, we're only looking back to T minus two.
Depends on how you're defining it. So you can either look back exactly 2 steps, or you can look back both step 1 and step 2 with a limited history cutoff. But yeah, in this case, the way that it's illustrated is just looking back 2 time steps. And that could be useful if you're modeling some kind of time series, like what is the traffic going to be like today? And that might make more sense to look back 7 days rather than 1 day. Because on Monday, the traffic will be more likely to be modeled by last Monday's traffic rather than Sunday's traffic. Yeah, so Sam points out in chat that genetics that skip a generation, something like that as well, could be modeled with something like this. So look at your grandparents' genetics rather than your parents' genetics for anything that skips a generation. Yeah, something like that. As an example of this, the probability of rain is the same every day. Is that actually true? Probably not. But we can now use a Markov representation of this to say, given that it rained yesterday, what is the probability that it rains today? So time homogeneous, it's not more likely to rain in the winter than it is in the summer, etc. There's not another layer of depth. The world isn't evolving. There's just a consistent probability of each of these events. Otherwise, we need additional probability tables for however the world is changing. We need to model that in another dimension, which grossly increases the complexity of the problem. But sometimes that's necessary to fully model the problem. The question is, how much information are you gaining from considering that additional dimension? If the probability of rain doesn't change much based on season, then maybe it's not worth the extra complexity of the model in order to model that small change in probability. You'll deal with the slight extra inefficiency and error from modeling rain as a single variable rather than try to account for it. And hey, your model is way fast. So we're going to dive into a fun, I don't know if fun is quite the right word, but an example here where we are locked in we work and live in a locked basement, and our boss is going to come into the office every day with either an umbrella or not an umbrella. And this is our only clue as to whether it is raining or not raining. So here we have a probability of rain at time t minus 1 is based on what is the probability of rain at time t given the rain at time t minus 1. So if it was raining at time t minus 1, the probability of rain is 0.7. If it was not raining at t minus 1, the probability of rain is 0.3. So this tells us that rain kind of appears in clumps. It's more likely that rainy days are followed by rainy days. And if it wasn't raining, it's more likely to continue to not rain, but not so much that the streaks are significant. 70%, 30% respectively. Then what is the probability of an umbrella? Given that it's raining, if it is raining, there's a 90% chance that our boss walks in with an umbrella. And if it is not raining, there's a 20% chance that our boss walks in with an umbrella. So that's a little strange. So we have a guess at whether it is raining or not based on whether our boss walks in with an umbrella or not. But it's not perfect. So Markov property certainly has some limitations. Do we see how this is a Markov property? We're only looking at rain yesterday to determine rain today. It doesn't matter what happened 2 days ago or 3 days ago or 4 days ago. We're just looking back 1 day. Whatever happened yesterday, that fully dictates the probability of what happens today. Now that is a simplifying assumption, but it's a simplifying assumption that can dramatically speed up our model. The question is just how much information is lost. So certainly some limitations. It can be an approximation of reality. How good of an approximation it is depends on the domain. So to what extent does rain today predict the probability of rain tomorrow? Any guesses as to the extent to which that is true? How accurate would that be?
During hurricane season, probably pretty accurate.
Yeah, there are certainly many more underlying factors. But if we were to come up with and look at a history of 1,000 years and just look at over time, did it rain on day 0? If it rained on day 0, did it rain on day 1? That would be an example. Then you look at rain on day 1, did it rain on day 2? That's another example. Did it rain on day 2? If it did it rain on day 3? It's another example. You just continue this all the way through 1,000 years. To what extent would the probability for that continue to be expressive of the probability of if it rains today, it would rain tomorrow? Is that cyclical? Are there other variables underlying that might help us to, at certain times or in certain temperatures or in certain locations, if it rained today, it's more likely to rain tomorrow? How well does just that one variable generalize, given that we're only looking at a history of one day? Or is there significant information missing from that other variables would help us to be able to account for? I don't have the answer to that question, but that's the kind of question that you want to think about when determining whether to model something as a Markov process or not. So wherever history is necessary, Markov property is a bad assumption. You should not use it in your model. Wherever history is actually important. Assuming that we are using a Markov approximation, how do we increase the accuracy? You could increase the order, account for some additional history, look back 2 days instead of 1 day, 3 days instead of 2 days. If you have the set of variables, you can start to incorporate more variables that says the probability of rain might be further accounted for by season. And now you add season as an additional variable in your, what is the probability that if it rained today and it is summer, it will rain tomorrow? What is the probability that you start to increase the number of variables in the problem? So adding season, adding temperature, adding humidity or pressure measurements could help to better predict rain. The question is, how much does that extra complexity actually add in terms of accuracy? So this becomes a big trade-off. This is very important when we start thinking about designing machine learning problems, and this becomes part of your feature selection. How important is the added complexity to the overall model accuracy? As you add more and more features, the model becomes much more complex, but you will start to be able to add additional accuracy to your model. If you strip out some of the existing variables, you might lose some accuracy, you might not, but is the trade-off worth it? But ideally, we have some self-sufficient set of variables. Of course, to be able to understand that, we have to know the underlying cause and effect of those processes, and that is another problem. Sometimes we don't have access to cause and effect. To what extent does season affect rain? To what extent does temperature affect rain? Humidity affect rain? If you don't have a way to answer those questions before we could actually measure those variables and be able to say something about it, we wouldn't necessarily be able to determine how effective each of them are at predicting rain. If we can directly measure things like season, temperature, humidity, burden is lessened. All right, let's look further at temporal models and how can we draw some conclusions from them. The first question we're going to want to answer is what's called either filtering or state estimation, depending on if you can use either one of them. So this says, what is the probability of the current measurement that we got given the history of observations? Given everything we've measured up till this point, how likely is the thing that we just witnessed? given that the history was rain, rain, not rain, not rain, 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 not rain, rain, not rain, not, etc. Up to the current day, and the current day we experience rain. How likely was that? So this helps us to keep track of the current state. As we do this, we can start to make rational decisions on this. So that is the state estimation problem or the filtering problem. There is the prediction problem. Given that we have measured up to today, can we predict what's going to happen tomorrow, or 2 days from now, or a week from now? Then the last one is smoothing, which allows us to take future observations and then make changes to the current observations based on the fact that we have a further sample. So this allows us to see the full history, given that we didn't have the information about tomorrow or the next day or the next day, but as we get that more information, the model is going to evolve because we have more information about more periods of time, and our estimates for what happened in the past are going to change based on the new information that we gather. So we can go back and smooth our estimates for predicting what happened in the past to help us to better be able to predict the future. So we call that smoothing. We have more evidence as we question and query more, so we can make better estimates for what happened based on more context. Future-looking context in addition to past-looking context. Then we have the most likely explanation problem. Given that we have a particular sequence of observations, we can query which states we went through. So as an example, maybe we have stormy and not stormy, and as this person in a bunker without the ability to look outside and see the associated weather, maybe we can estimate the probability that a hurricane was passing over us or not based on the number of straight days of rain, the straight amount of rain, stormy and not stormy. And so we would go between these two states. It is stormy, so it's affecting multiple days worth of rain. It's not stormy. And we could determine, given that we saw rain 4 straight days here and 4 straight days here, there was storm here, no storm here, storm here. And that allowed us to find the most likely path of when those storms passed over us, how many storms were there, etc. So that is the most likely explanation problem. So tons of applications for most likely explanation. You can imagine you're designing an LLM. What is the most likely sequence of words to generate that are going to make sense or respond to a user's query? You could reconstruct bit strings given some noise. So you're passing some information over a network, and some of that, there's noise associated from that, and a couple of bits get flipped. You can go back and try to understand what is the most likely data that was sent over the network, given that when we try to reconstruct the data, it fails. So we're going to go into a little bit more detail on each one of these problems and talk about exactly how to calculate state estimations, so filtering, prediction, smoothing, and most likely explanation. We have some algorithms for a couple of these, and in general, just how do we calculate these questions. So let's start with filtering. And what fun would this be if we didn't start this with a bad approach? So remember that the filtering problem is the probability of the current observation given the history of evidence. So we make an observation and we want to say, given the history, how likely is it that we saw what we saw, given our best estimate for what should have happened in this state. So that approach, given the new evidence data, recalculate the probability of the current observations given the entire history of evidence. The reason this is bad is we're looking at the entire history of evidence every single time, and it's going to get more and more complicated to compute that as we get more and more data. So each update that we apply is going to be more and more expensive than the last one, new one more expensive than the last one, etc. Instead, we should maintain a state estimate and update it given the new observations. So we're gonna come up with a model of how likely it is to be in a particular state. Given that we see a new piece of evidence, we are now going to utilize that new piece of evidence to update the existing model. And that means that every single update has the same complexity, the same computational complexity, no matter how long that history happens to be. Does that make sense? If we do the same thing every time, then an update in 1,000 years won't be any more computationally expensive than the very first update. So we call this recursive estimation, and it's not perfect, but in the big picture, you have one big variable of control, the learning rate. How much are you updating based on each new piece of information? You could say that the entire rest of the history has 95% weight, and the new single data point that we get will change the model with weight 5%. That would be an interesting way to grade a class. Your current grade can change by up to 5% based on your performance on the next grade item in the class. So you get 100% on something, I'll add 5% to your grade. You get 0% on something, I will take off 5% of your grade. Something like you can get plus or minus a certain amount based on the quality of your most recent submission. And that can balloon you closer to 100%. It can start to tail off, but it summarizes your history of performance based on that. So that's recursive estimation. The probability of the variables, so remember that X is just it's the vector of evidence variables at time t+1, given the evidence, that is the history of evidence from time 1 to time t+1. That's the question that we're trying to answer with the filtering problem. So it's time t+1. What is the probability of whatever it is that we measured? So what is the probability of rain at time t+1 given the history of rain? But we use bold here because there may be multiple variables embedded in that observation list. So if that's a function that's based on the evidence, the history of evidence from time at time t+1, not times. There are two pieces of evidence. At time t+1 and the probability that we saw what we did at time t given all of the evidence up to time t. So that is some function of that. I feel like I didn't explain that. Let's give this an example. So here is our history. We start at time 0 and we get up to time t. This is just our history of rain or not rain or whatever else we have. And then there's one new data point at time t+1. The value that goes here, the probability that should be some probability distribution here. So we're gonna have rain and no rain as a probability. The probability of that, given this entire history, is a function of the evidence, whether we got rain or no rain here. And the probability that we got the observation that we did here, rain or no rain, given all of this. So this is that Markov assumption, saying that with some function, we can convert this history deriving this value to this history deriving this value. What is that function? How does it evolve with this one new data point that we acquire? You could say something like the function is we take 5% of the weight of what we saw here and 95% of the weight of what we saw here, combine that, and that is the function that derives the new probability of rain and not rain, given the additional evidence that we got. And that is now independent of how long this history is. Questions on that? Does that help clarify? I feel like that's a bit better than I explained it the first time. Yeah.
So does that keep happening then? You check.
Yeah. Yeah, the function is going to be, so at time t+2, we're going to be looking at the history all the way through time t+1 and etc. But it's a way of now saying, how can we answer the question of what is the probability of the current event that we saw given the history? And it's going to be based on a recursive definition based on the old history of up to time, the last time step, which is recursively defined, which is recursively defined, which is recursively defined. But now it's the entire history is embedded in that one calculation. I never know what goes on up there to cause this to go like that.
Isn't that the train? Someone said one day, like, if she could
Oh.
go by, it like shakes the foundation a little bit somehow.
That's
It's because somebody's stepping through there.
Yeah, I just heard somebody said,
Yeah.
It's an office.
That's your office.
Yeah, exactly. Someone's in my office right now.
Yeah,
Yeah.
get a lot
Yeah,
of bang up there.
yeah,
We can take a
exactly.
break and find out.
She'll find it.
Maybe Tony.
All of the worst. So, how do we do that recursive estimation? Part one, we're gonna project the current state distribution forward from time t to time t plus one. That's gonna get some amount of weight, and then part two updates the state distribution using the new evidence. So let's give you an example of how that would work. So just like we have up above, we divide up the evidence. So the evidence is now, since we have a value for time t plus one, we have a distinction between the evidence of time t and time t plus one. Then we use Bayes' rule. So we go from effect given cause to cause given effect. And then we use the Markov assumption to say that we only have to look back one step to be able to do that. And then we get the associated, we can break this into the update and the prediction, which we then multiply together and then fill it to have probability density 1, and we get the new probability of rain and not rain, given that new data point. So in general, you could just utilize the last point here as the update. So this is just how it's derived, but the end rule is that you have the update times the prediction times the alpha scaling factor that gives it probability density 1. And so you get this in general. We're going to now sum over every evidence variable. And we can factor out that sum. Again, what's nice about this is everything is the same regardless of how long that history is. So we have the recursion of the old work, then we have the transition model of how likely are we to move from to see the current evidence variables given the evidence variables that we saw in the last time step. That's the transition model. We look at that for every possible evidence variable. Then we go through the sensor model that says, given that we experienced rain or not rain, what is the probability that we saw the umbrella or not the umbrella? So let's go through the example of the umbrella to see this actually play out. So we know each day it either rains or it doesn't. And since we are now in this bunker, a basement with no view of the outside world, we have to use as evidence whether our boss comes in with an umbrella or without an umbrella to be able to make that decision. So we're going to start with no information on day 0, no observation. We just decided we're going to use this umbrella as a way of modeling our understanding of rain or not rain in the outside world. So no observations. So we have to make a guess as the probability of rain. So the probability of rain is going to start out historically to be 50-50 because we don't know, and hopefully over time as we see umbrella and not umbrella, we can start to get a better sense of how likely it is to be raining. So on day 1, we observe that umbrella equals true. Our boss comes in with an umbrella. So we go through step 1, the prediction step first. We know that we've set this to 50%, 50%, and we know that the probability of, we look over the history of our variables, which doesn't have much right now, but we know there's a 70% chance if we go back to a setup of the problem. Back. Should have put this closer, there we go. The probability of rain on the next day, given the rain on the previous day, this is where the 70%, 30% are coming from. Are back here. So the probability of rain, given that it rained, probability of rain that it didn't rain, 70%, 30%. Rather than go back through all the slides, I'm just going to find where we were. Do that here. So that's our prediction because we are basing it on almost no evidence. So we see from this that the step 2 now is going to be the update. And it allows us to plug in the actual evidence that we saw. And we see that as a result, once we scale the 0.45 and the 0.1 to have density 1, that our new estimate is that there is an 81.8% chance of rain and an 18.2% chance of no rain. So we updated based on the evidence that we saw. On day 2, we observe umbrella again. So we can step 1, but now we are basing this on our history. So we can see that we're plugging in, instead of 0.5 and 0.5 like we did before, we're plugging in what we had before, 0.818, 0.8182. And that allows us to derive the new prediction. And then from the new prediction, we derive our update. And that gives us a new update of 88.3% and 11.7% for rain and not rain. Given that we have umbrella on day 1 and umbrella on day 2. And this would continue with more and more evidence to compound and start to estimate the true probability once we had enough history of observation.
So the 0.3 and 0.7 are the probabilities you have from your entire history calculation.
There are probabilities of, we have some way of knowing the probability of rain given rain the last day. And no rain given no rain the last day. So. It's very hard if you don't have that. All right, prediction exactly like filtering, but there's no new evidence because we're trying to predict into the future. So instead of being able to say how likely was the event that we just saw. So yeah, here this was the probabilities that it rained on that day. There was an 82% chance that it rained on the first day, and there was an 88% chance that it rained on the second day, given that we saw the umbrella. Now we care about actually predicting into the future. What is the probability of, given everything that we saw, that it is going to rain tomorrow? So you can start predicting not just the next day, but as far into the future as you want, given the history of evidence that you have. This gets a little bit harder to predict further and further into the future because there become more and more unknowns. So here it's exactly the same thing, except there's no additional evidence for time t+1. The goal is to calculate the probability of rain at time t+1 given the evidence up to time t. We should first talk about the concept of a stationary distribution. This is just saying that the transition model reaches a point far enough in the future that predicting further doesn't change the distribution. This makes sense. There's no amount of rain that we could see if we looked far enough into the future that would change our underlying model of how likely it is that it will rain tomorrow, given that it rained today. Kind of the point of no return with regards to the law of large numbers. There is the mixing time, how long it takes for a Markov process to reach its stationary distribution. And we find that even a small percentage of the way into the mixing time in the future starts to have a very poor performance in terms of actually predicting what's going to happen. So this is very useful for predicting very short into the future, and that drops off quite quickly. So the mixing time can help us to figure out exactly how far we can look before we can figure out, or we can assume that the performance drops off significantly. So if the mixing time is very long, then we can start to look a little bit more into the history. If the mixing time is very short, then even 2 or 3 steps ahead may be obfuscated by lack of data. To do this, we use the exact opposite of the backward recursion that we used to identify the probability of the current time step, given the history of time steps. So we use what's called forward recursion. This is going to look into the future based on unknown values. But if we say the probability of rain, we can set that rain happened on that day. And then we can start to recurse backwards to say, well, if it rained on that day, what is the probability that it rained the day before? Knowing that probability of it rained the day before caused the rain on the last day. And you can do the same thing for not raining on the destination day. And then you get a distribution of the probability of it rained on that day or not rained on that day by setting up effect given cause, effect given cause, effect given cause, and propagating that all the way back to the current time step.
Sorry.
Yeah,
Going back to prediction, wouldn't it more likely scenario be like, instead of saying that it will rain so and so days to the future, would it be more like it rained on this day now, in 1 year's time, it will rain again this day?
yeah,
It's long.
yeah, well, you could start being able to predict further and further out into the future, given that mixing time, but yeah, if we've only collected 3 days worth of information, then we can't be very sure at all of what it's gonna look like in a year.
Correct, but wouldn't it be more applicable, or like saying that something that happened on this day will happen again next year?
Yeah, we'd have to use time series to effectively model that. We'd have to understand the length of the cycles. The fact that that prediction being a year ago, it relies on a concept of seasons and the length of time it takes the Earth to revolve around the sun, et cetera. So you'd have to model that in a time series.
Okay, but would that include better predictability?
Oh, yeah.
Certainty, rather than saying simply this many days, today?
Quite possibly. That's gonna be domain specific though, because now if we're looking at the probability that. I don't know what a good example would be, but something that doesn't cycle on a yearly basis. Then a different domain would have a different set of cycles to it, or it requires our understanding of the underlying problem. Yeah, so forward recursion is exactly like backward recursion. So how likely was it that this model generated this history of data is the question we're going to be asking. We can compare different models to figure out which one would be most likely to produce the same data. Of course, in practice, since we're summing so many, we're multiplying so many probabilities. And then we get the underflow issue, so we're multiplying so many numbers over and over and over and over to come up with that history of data. And since they're probabilities, they're all something that's less than 0. So a float only stores so much, a double only stores so much that you can only multiply so many probabilities before you lose some amount of significant figures in that. And you'll lose, eventually you'll just reach 0, where even a double thinks that with a long enough history, the probability of anything happening is 0. So to handle this in process, in practice, we need to be able to use log arithmetic, where you go from multiplying a bunch of things together to adding the logs of things, which can actually represent that level of underflow by just using exponentiation. Have we experienced that before in any classes, or have we seen how to handle underflow mathematically? Whenever you're multiplying probabilities together, it's much better to look at them in terms of the subtraction of logarithms. Why don't we take a quick break before we dive into smoothing? It's been just about an hour. So let's come back in somewhere between 5 and 10 minutes. Stretch your legs. All right, diving back into it. 6 more slides, we can do it. So smoothing, remember that smoothing is, we're now utilizing some additional evidence that we've collected. So at the time we made the prediction for day 11, it was based on the history of days 1 through 10. But let's say now that we collect information up through day 20, the question is, given all of that history, now can we go back and re-predict what happened in day 11? Or relearn some additional information about what happened in day 11 based on the longer history that we have now collected evidence for. So we're going to split the evidence into 2 parts, from time 1 to k, which was used for that prediction, and from time k to t, where k is the past state, t is the current state, and we can now split this into those chunks. So again, a way to calculate this based on this, we end up with an f and a b from 1 to k, and from k to k plus 1 to t. So this is a recursive process running backwards from time t to k. That allows us to, we use recursion to calculate from 1 to t, we use backwards recursion to go from t back to k, sorry, 1 to k and t to k. So kind of meeting in the middle. Backwards vector starts with all ones, since the evidence is empty, probability of observing whatever it is that we observed at time t equals 20, now that we're at that point, is 1, we observed it. So then we just calculate. Hey, wasn't done with that yet. Try to zoom in. There we go. This allows us to now have values for the sensor model, the recursion, and the transition model in this case, where we now are looking from based on time k. K is that middle point. So the sensor model has everything based on the evidence at time k plus 1. The recursion allows us to go from t back to k, and the transition model now is looking for predicting k based on k plus 1. So that uses that backwards recursion, where the destination is now based on the evidence that we've collected since then. Let's give you an example of that. Back to the umbrella world. We could apply smoothing to the probability that it rained on day 1, which we know that it did. Given the history that it rained on both days 1 and 2, this would be the smoothing of once we observe day 2, we can go back and improve the accuracy of the probability that it rained on day 1, given that we saw both an umbrella on day 1 and day 2. So from filtering, we'll just plug in the 0.818 and 0.182 with probability of it rained and it didn't rain, given the umbrella that we saw. Then we can initialize to 1 and backwards recurse. So this is exactly what we did, is we built forwards, and we find that we get 0.69 and 0.41 from the first part. And plugging that in, we now can find that we go from 0.818 and 0.182 to 0.883 and 0.117. So it became more likely that it rained, given that it rained on days 1, or given that we saw umbrella on day 1 and 2. And the reason it got more likely is that there was that 70% chance that given that it rains on a day, it rains on the next day. So now that we have 2 straight days where we saw umbrellas, and because there's a 90% chance of seeing an umbrella on a day that it rains, and a 20% chance of seeing an umbrella on days that it doesn't rain, given that we saw umbrellas on both days, now the 70% chance that it's likely that if it rained on one day, it rains on the next day kicks in, and we're able to see that this more likely scenario means that it was more likely that it rained on the first day. I already answered the question that I planned to ask you. Oops. Did not mean to do that, but here we are. Yeah, so the fact we saw an umbrella on day 2 makes it more likely that it rained on day 2. Since our model sees rain is more likely to persist across days, there was that 70% chance that it rains on one day, it rains on the next. It was more likely to have rained on day 1. This is useful if we ever want to, let's say on day 2, we want to predict what happens on day 3. If we have a better estimate of the probability of rain on day 1 and the probability of rain on day 2, we can now use that history to move forward a better estimate of the probability that it rains tomorrow, given that it is day 2, which can build just a better model of rain in general.
This just sounds all in script.
So calculations again for backwards recursion take constant amount of time per step, linear per calculation, which is not bad. If we use dynamic programming and store this as we go, so we're not recalculating anything, the entire history of smoothing can be done in linear time, which is really cool. And this gives us what we call the forward-backward algorithm, where we use forward recursion and backward recursion to smooth over time step k based on a history of evidence from 1 to t, where k is before t. And here is that algorithm. So forward backward is what is used for smoothing. The last question we want to answer, any questions before we dive into the most likely sequence and the Viterbi algorithm? Right. So let's say in the first 5 days, we observe umbrella, umbrella, no umbrella, umbrella, umbrella. There are 2 to the 5th possible weather sequences. Maybe rain, 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 not rain. There are 2 to the 5th possible sequences of rain and not rain. What is the most likely weather sequence that explains this sequence of umbrellas that we have seen on the 5 days? This breaks down really into a question of the lack of umbrella on day 3. Does that mean that it was raining and the person forgot the umbrella on that day? Or was it not raining and we switched from raining to not raining and then back to raining in a single day? Which one of those more likely explains the fact that we didn't see an umbrella on day 3? If it wasn't raining on day 3, then was the umbrella on day 4 precautionary, or was it actually raining on day 4 again? So we could enumerate all possibilities and calculate their likelihoods directly. That seems silly. If we just care about what is the most likely explanation for this sequence of events. If we enumerate every possibility and just take the maximum of all 2 to the 5th, what happens if instead of a history of 5, we have a history of size 1000? Then we would have 2 to the 1000 possibilities to directly calculate, and that is never going to finish. So instead, we could use smoothing, finding the posterior at each time step, but that's greedy and may not actually return the most likely path. So what we want to use is a dynamic programming algorithm called Viterbi. So whenever you have a hidden Markov model, which is exactly what this structure is called, when we have a probability of when it rains, what's the probability that it rains on the next day and doesn't rain on the next day, given that it's not raining, what is the probability that it rains on the next day or doesn't rain on the next day? That's a hidden Markov model where we don't know the value of rain or not rain, but we can figure out based on umbrella how likely it is that it was raining when we did it. So it's a temporal probabilistic model. The state of the process is described by a single discrete random variable. So umbrella determining rain. In general, we don't know which state we are in, raining or not raining, but we know the approximate probability based on some measurable evidence like umbrella. So that is called a hidden Markov model because again, what's hidden is the state that we are in. And rather than describe Viterbi, I found a very good reference to Viterbi that I want to show people because it goes over it in a level of depth that I think is appropriate, given that this is a very survey level course on a lot of these algorithms, introducing them to you at a very basic level. We're not implementing all of these as we go. So we're going to, actually, I already had this loaded, but this is going to use an example for Viterbi that I have seen a lot. And this is calculating gene expressions. So we have two states, the high and low, and we see an associated transition probability between high and low. So this is the history that we know based on the evidence. These are the associated transition probabilities. But as we do this, what we see is a particular sequence of A's, C's, G's, and T's. So what we see is GGCACTGAA. And now the question is, what is the most likely path through this hidden Markov model based on the fact that this is what we saw? We saw this sequence. What transitions between high and low most likely generated this sequence? So we could go through, what is the probability of that we were in high, 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 high for the 9-character sequence. We could figure out high, 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 low, and calculate all 2 to the 9th possible values. Instead, we could use Viterbi. We could use Viterbi, use dynamic programming, and calculate this, it turns out, in linear time. So the probability that a particular path is chosen would be, let's say, what is the probability that the G came from the high versus the low? Well, we just look at starting. There's a 50% chance that we start in high and a 50% chance that we start in low. Given that we start in high, the probability that the first character is a G is 30%. Given that we started in low, the probability that the first character is a G is a 20%. But we don't know where we started. Given that we were in high, there's a 50% chance that we stay in high and a 50% chance that we move to low. Given that we're in low, there's a 60% chance that we stay in low and a 40% chance that we move to high. But the next character we saw is a G. Is it more likely that we started in high, stayed in high, started in high, moved to low, started in low, moved to high, started in low, stayed in low? How could we calculate that? We could go through just looking at the first 2 characters. If we did this, we could calculate them all directly since there aren't very many of them. There are only 4 possibilities at this stage. Guesses as to the most likely path if we just saw the sequence that was the first 2 characters. What probabilistically is the highest there?
Started in on saving.
Yeah, I think so. That makes the most sense to me. There are 4 options. We either started in high, which is 0.5, times we express the first G, 0.3, times we stay in high, 0.5, times we see the second G, 0.3. We could have started in high, expressed the G, transitioned to low, which is 0.5, and then expressed the G from low. We can see that this is higher than that. So that's not going to be the best or most likely path. We could have started in low, that's that transition probability, expressed the G in low, transitioned to high, and expressed in high. This is transition to high was 0.4, not 0.6. Is that higher than this? This is lower than that, and this is lower than that. Everything else is the same. So no way this could be the right answer. Or we started in low, expressed in low, stayed in low, expressed in low again. Is that higher or lower than the first one? That's also lower, but you'd have to calculate it out to be absolutely sure. It is lower. So the best path, the most likely path is right there, that we started in high, express the G, stayed in high, express the G. This is when we say given the evidence, the only things we care about are any paths through this that express two Gs. We don't care about the probability of expressing an A or expressing a C, given that the sequence that we saw is just GG.
So is that the actual Kirby algorithm?
No, this is just going through it and getting a sense of, yeah, I'm not explaining to Turby yet. This is just getting you the ability to read the HMM and make some calculations based on the associated probability. Yeah, this is not dynamic. We haven't actually started to store anything, cache anything, and use anything that we've stored yet. Questions on how to read this or how to come up with a basic probability? You can see that as you're starting to multiply probabilities together, this gets lower and lower and lower and lower. And you can imagine if this sequence were the actual human genome or something that's significantly longer than 9 characters, how you would very quickly underflow even a double, which is why you need to utilize log probabilities. All right. So the Turby is going to keep track of a table. And the table is going to be calculated dynamically. So the first thing to note is that how to fill something that is in the middle of this. So what is the probability that the most probable path ended with an A in this point? Like, what is the probability that we expressed an A given that we expressed a GGC before it? So we look at the associated probabilities of whatever the possible paths were to produce GGC, either that ended in high or ended in low. So to calculate this, that's going to be the possible ways to do this, either that ended in high or that ended in low. And the only way we care to express this is the most likely path that ended in high or the most likely path that ended in low. We don't need to consider any other path of what generated GGC, just the most likely path that ended in high, the most likely path that ended in low. And then we can look at what is the probability that we stayed in high, what is the probability that we changed to low, what is the probability that we went from low to high and low to low. We just calculate those associated probabilities of going from the most likely path here that ended in high, and then take the maximum of this and that becomes the new best path that got to high from each of those. So you're going to get rid of some of these arrows as you calculate the probability for the next. And that will just kind of extend this to say, well, this now extended here, and this one moved up to here. And nothing is in low at this point. And then that's the new most likely path. And then you have a new high and a new low, and you'll calculate again, given those 4 things. And you'll figure out which arrows stick and which ones don't. And you can see that for each step, it's actually a constant number of operations based on the last step. So you cache this result as you go and build up the most likely path as you consider each new character, each new character, each new character. So that's all this is saying is the max over all of the possibilities based on the most likely path that you saw up to the past point. At point x minus 1, the most likely path that you've seen up to that point. So that's how you calculate it for a given one. And then once you get all the way to the end, the maximum path has already been calculated. So do we see how this is basically quadratic in complexity? Does that compute? For each cell, for each character, for each one of these, which is 2 loops, we're going to have one thing to fill that will always take 4 operations. Let's get down to the table. So they do this all in log probabilities because that's easier to store, but you can start to see that this just maps to probabilities to just, again, log base 2 probabilities. And I want to show you the table, which is right here. We just start filling in the table and then we ask, okay, given that we are at this cell on the table, where did we come from? So it stores a history. By the time we see the maximum probability, which is the equivalent of 2 to the negative 24th probability, that's going to be larger than 2 to the minus 25th. So now we just follow backwards the associated arrows, and that will tell us that the probability, the maximum probability was generated from going high, 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 low, 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 low to generate that. So every time you calculate a new cell, you're going to look at, okay, if we were here and stayed in high, if we were here and went from low to high, take the maximum of those, whichever one the maximum is, write the value here and point the arrow back to where you came from to generate this value. Does that make sense? No information. So you start here. What is the probability that this first G was generated from H, which is 0.5, 2 to the minus 1 is 0.5, times 2 to the minus 1.737. So here, express that. And you see that now it's just an addition. If you add minus 1 and minus 1.737, you get minus 2.73737. So it's just addition now instead of multiplication. And addition of negative numbers aren't going to overflow an integer faster than your multiplication is going to underflow a double. Because you're already calculating it in terms of an exponent. So that's the probability that the first G is expressed from high. This is the probability that the first G is expressed from low. You get minus 1 plus minus 2.322, gives you minus 3.322. Then to calculate this cell, we say, all right, this could either come from here or it could come from here. Either the first G was produced by H, then we stayed in H and produced the G again. Or we were in low with that associated probability and we stayed, or sorry, we transitioned to high and then expressed the G from high. Whichever one is the maximum of those values, it gets written here. And we point the arrow back from which one it came from. It turns out it's more likely that this GG was expressed coming from high than it was coming from low. Then we move on to this cell. And we calculate this cell. And it's more likely that if this second G came from low, that the first G came from high. So it's more likely to go this path to generate this G than it is to go this path and generate the G. And that value gets written here, and the backtracking arrow says this came from high. Then we go to this cell, and you see that this isn't based on a long history, we're only looking at the last step. This becomes a Markov process. We don't care about the entire history, we're just using the cached value to say, what was the most likely path to generate this cell? How does it affect the next cell? What's the most likely way to generate this cell? Where did it come from in the last time step? You continue to do that, filling out every cell until you reach the end of your query, and that tells you the most likely path through this without having to go through every possibility. You can see that how many ways are there through this? There are 2 to the 9th possible ways through it, but how many ways did we end up actually calculating? Instead of 2 to the 9th, we had 18 values. Each of those 18 values had potentially 2 lookups. 36 is way less than 2 to the 9th, 512. So it's a massive speed up over the exponential brute force to be able to use dynamic programming, even in a small example like this, it's a 10 times speed up. More than a 10 times speed up. And a tiny little toy example like this. It would just get more and more and more profound as you pronounced, as you get longer and longer strings, or have the ability to have more states than just high and low. Yeah.
Why would you use Viterbi over the backward forward?
So they ask different questions. Backward forward was for smoothing. This is for the most likely path, the most probable path through an HMM. Great question. Yeah, so this tells you what the most probable path is, and you can easily reconstruct that. The probability is 2 to the minus 24th. And you can convert that back into base 10 if you want to give you the associated probability in base 10. Base 2 is used just so that you can add the associated probabilities very easily. So you convert everything into base 2, do the associated subtraction, convert back to base 10 to report your answer. So that's really all I wanted to show. And then there's the forward algorithm with an example and the backward algorithm with an example. So kind of. This is a good resource, but I thought that it would be nice to visually just show you what Viterbi looks like rather than create my own example. Any questions about Viterbi before we go back to other things? So yeah, it's just a dynamic programming algorithm. It's not really more complicated than any other dynamic programming algorithm that you've seen before.
Is there a reason why we're focusing around Viterbi versus the other one then, or is it just like the?
They solve separate problems.
Okay.
So if we go back to this deck. Is that the right one to go on? Yeah, so forward backward is solving the.
Right, so you were saying that it's just a dynamic programming algorithm.
Yeah.
And there are other ones that are similar to this. Is
Yeah.
there a reason why we're focusing on this one specifically?
So yeah, Viterbi is the best way to calculate this. Forward backward is the best way to do smoothing. Viterbi is the best way to do most likely through an HMM. So that's Viterbi. We can certainly model 2 or more random variables. There was only one that we showed in the HMM that we went over at the moment. But yeah, if you combine variables into what we call a single mega variable, and the values of that are all possible combinations of the individual states, then we have one variable representing multiple variables. It would be something like if you have a day of the week, hour of the day, we just come up with a tuple that is Monday at 9, Tuesday or Monday at 10, Monday at 11, Monday at 12, and you have each tuple, and you have a mega variable representing of those variables. And then you could have an HMM over that variable. That single state, though, does not apply, that restriction doesn't apply to evidence variables. Evidence variables can also be continuous, so we don't have the discrete requirement on evidence variables, we just do on that query variable. There are some speedups that are available if you want to try to represent the transition model as a matrix, the number of possible states and dimensions. And then your forward and backward messages for forward and backward recursion are represented by column vectors in that matrix so that you can multiply them easily. Sensor model is a diagonal observation matrix, and then computations are matrix vector operations, which are much faster than other operations. And that works very well. There's your forward algorithm, your forward recursion, there's your backward recursion in terms of matrix vector multiplication. And this is used or most useful when we apply this to what we're going to call Kalman filters. Has anyone heard of a Kalman filter before? One person, or greater.
I don't remember what it is.
Relearn. So Kalman filters filter using continuous variables where measurements are discrete or noisy or at irregular intervals or imprecise intervals. And then instead of the discrete calculations of hidden Markov models, you have calculus. So of course, I don't necessarily want to go into all of that detail because it's significantly messier than what we've talked about so far. But you can see from this, I'll zoom in on this so you can see this a bit better. There's filtering and smoothing for a two-dimensional variable for this. So an object is moving on the XY plane, and there's the true trajectory, and there's the trajectory that is based on the noisy observations from it. So you can use Kalman filtering because this is happening in real time, even though there are discrete intervals, you can go back to this and apply smoothing so that what we look at is we estimate this took some kind of parabolic. It'd be like throwing something in straight out and it curves down to the ground based on gravity. So the filter would go and based on those noisy observations, predict that what is most likely to have occurred from that is some kind of parabolic shape. So mostly just want to introduce you to the idea of a Kalman filter in case you ever want to implement one. This is what it is, this is what it's called, and this is what it does. But underneath the hood, lots of calculus. How are we doing? Any questions on anything covered?
That seems already straightforward.
Yeah,
Super understandable.
this is nice and vague, which is why. Yeah, but this is everything that I have prepped at the moment for at least animated. I could launch the next slide deck, which is done, but there's nothing that reveals things slowly over time. Any votes for going over the start of that versus going home and covering this next time? All right, yeah, going home and covering it next time. David, I at least got one vote for that. Multiple votes for that. Someone putting on a coat already. Anyone who would rather stick around and see the start of a machine learning slide deck?
Or it's better with schedule, but that's about it.
I really appreciate your fade-ins on that. I think I'll wait to see.
Yeah, yeah, smart. All right, yeah, we'll come back to this on after the exam on Tuesday. All right, have a good weekend. Get lots of studying done. Reach out to me if you have any questions.
It's the,